Ever wondered how polymorphism is achieved in object-oriented programming? The answer lies in virtual functions. Let's break it down. In the world of programming, a virtual function is a special kind of function declared in a base class with the virtual keyword. It's designed to be overridden or redefined by derived classes. This gives derived classes the ability to provide their own unique implementations of the function. The core of its purpose: to pave the way for dynamic or late binding. This is a fancy way of saying that the appropriate function implementation is selected at runtime. In simpler terms, it allows the program to decide which function to execute while it's running. So when we're talking about polymorphism, we're really talking about the ability to treat objects of different classes as objects of a common base class. In essence, virtual functions are the backbone of polymorphism, allowing objects of different classes to be treated as objects of a common base class. Now that we understand virtual functions, let's delve into dynamic binding, a concept closely related to virtual functions. Dynamic binding, often referred to as late binding, is a mechanism that allows us to decide which function implementation to use at runtime rather than at compile time. This is crucial in object-oriented programming as it enables us to treat objects of different classes as if they were objects of a common base class. But how does this happen? Well, the magic lies in the use of virtual functions. Let's break it down. When a function call is made through a base class pointer or reference that points to a derived class object, we don't know until runtime which function will be called. This is because the function call is bound dynamically to the function body. Imagine you're at a coffee shop and you order a latte. The barista in this case acts like a base class. When you place your order, the barista doesn't know exactly how to make your drink until they check the recipe, which is like our derived class. The order or function call is made, but the specific instructions or function body aren't determined until the barista checks the recipe. This is dynamic binding in a nutshell. Dynamic binding is particularly powerful when used with inheritance hierarchies. It allows us to write more generic, reusable code. We can define a common interface in the base class and have each derived class provide its own implementation. This is where virtual functions come in. By declaring a function as virtual in the base class, we're saying, hey, this function is likely to be overridden in a derived class. This signals to the compiler that we want dynamic binding for this function. So in essence, dynamic binding and virtual functions go hand in hand. Dynamic binding provides the flexibility to decide which function implementation to use at runtime, and virtual functions provide the mechanism to achieve this. So, dynamic binding is the mechanism that selects the right function implementation at runtime, powered by virtual functions. From virtual functions, we move on to pure virtual functions. But what exactly are they? Well, pure virtual functions are virtual functions that don't have an implementation in the base class. Instead, they are declared with the intent of being overridden in any derived class. These functions are typically declared by appending =0 to the virtual function declaration in the base class. In essence, pure virtual functions provide a blueprint for the derived classes, setting the expectation for certain functionalities that the derived classes should embody. The base class in this case is often referred to as an abstract class, and interestingly, you cannot create instances of an abstract class. But why is that? It's because the abstract class is incomplete by itself. It's like a jigsaw puzzle with missing pieces. The pieces in this case are the pure virtual functions that need to be defined or filled in by the derived classes. Since the abstract class is incomplete, it doesn't make sense to create objects from it. However, these abstract classes are incredibly useful as they provide a common interface for all derived classes. They define a general form that all derived classes should take, ensuring a level of consistency across all derived classes. Let's consider a simple example. Let's say we have an abstract class shape with a pure virtual function calculate area. Any class that derives from shape, like circle or rectangle, would need to provide its own implementation of calculate area. In this way, even though circle and rectangle are different shapes, they share a common interface through the shape class. In summary, pure virtual functions are a powerful tool in the world of object-oriented programming. They allow us to define a common interface that all derived classes must adhere to. This leads to more consistent, modular, and maintainable code. Pure virtual functions, therefore, help define a blueprint for derived classes. facilitating the creation of abstract classes. In C++, the override keyword plays a critical role when dealing with virtual functions. But how does it work? Well, let's dive right in. The override keyword, as the name suggests, is used to explicitly indicate that a function in a derived class is intended to override a virtual function from the base class. Think of it as a clear signal to both the compiler and the programmer that the function is meant to replace the implementation of a function with the same signature in the base class. Now, why is this important? The answer lies in the concept of polymorphism. When a derived class overrides a virtual function from the base class, it provides its own unique implementation of that function. This allows an object of the derived class to behave differently from an object of the base class when the same function is called, a key aspect of runtime polymorphism. But here's the catch. Without the override keyword, if the function signature in the derived class doesn't match exactly with the one in the base class, the compiler won't raise a flag. This could potentially lead to unintended behavior in the code, as the derived class might end up not overriding the intended function, but rather introducing a new one. That's where the override keyword steps in. When you mark a function with the override keyword in a derived class, you're telling the compiler, hey, I'm intending to override a function from the base class. If there's no such function to override, let me know. So if there's any mismatch between the function signatures, the compiler will throw an error, helping you catch and fix the issue during the compilation phase, rather than dealing with unexpected behavior at runtime. In essence, the override keyword in C++ serves as a safety net. It helps ensure that the function in the derived class indeed overrides a virtual function in the base class, allowing you to leverage the power of polymorphism with confidence. The override keyword in C++ is a safety net, ensuring that the function in the derived class indeed overrides a virtual function in the base class. Finally, let's tie everything together and see how virtual functions enable polymorphism. Polymorphism, a Greek word meaning many shapes, is a keystone concept in object-oriented programming. It allows us to treat objects of different types as if they're objects of a common base type. In other words, it enables us to write more generalized and reusable code. Now, how do virtual functions come into play? Well, virtual functions are the magic behind this ability. When we declare a function as virtual in a base class, we're saying, hey, this function might be implemented differently in the classes that inherit from me. This opens the door for dynamic binding, where the correct function implementation is determined at runtime. Imagine we have a base class called shape and two derived classes, circle and rectangle. In the shape class, we have a virtual function called draw. Now, circle and rectangle each have their own unique way of drawing on screen. By making draw a virtual function in the base class, shape, we allow the circle and rectangle classes to provide their own implementations of draw. This is where polymorphism shines. We can have a list of shape pointers, and each one could point to an object of type circle or rectangle. When we loop through the list and call the draw function on each shape pointer, the appropriate draw function, be it from circle or rectangle, gets called. This is all thanks to virtual functions and dynamic binding. The beauty of this approach is that if we later decide to add a new shape, say a triangle, all we need to do is create a triangle class that inherits from shape and provide a triangle-specific implementation of draw. We don't need to change any of our existing code that deals with shapes. Virtual functions are the linchpin of polymorphism, providing the flexibility and extensibility needed in class hierarchies. They are a powerful tool in our programming arsenal, enabling us to write more maintainable, modular, and reusable code. As we wrap up, let's recap the key points about virtual functions. Primarily found in languages like C++, these functions are crucial for achieving polymorphism, allowing objects of different classes to be treated as objects of a common base class. We've learned that a virtual function is declared in a base class and intended to be overridden by derived classes. This enables dynamic binding or late binding, which determines the correct function implementation at runtime. We've also explored pure virtual functions, which are declared without any implementation in the base class, making it an abstract class. Objects can't be instantiated from these abstract classes, but they provide an interface for derived classes to implement. We've also touched on the override keyword in C++, which helps catch errors during compilation. All these elements come together to enable polymorphism, making code more flexible, extensible, and maintainable. Remember, virtual functions are a powerful tool in object-oriented programming, facilitating modular and maintainable code through polymorphism.